Okay, so I'm gonna switch the topic slightly and discuss scope function and information, visual information. So, s- so partial derivative of the log density function is important, and we call it a scope function. So whatever is important should have a name. So that means scope function is a very important one. Another one, which was first sort of by R.A. Fisher, is the Fisher information function, which is a curvature of the log density. Okay, so this is the kind of density function, right? Log density. So this is a scope function, and then curvature means the how fast they change. So this one supposed to be negative, right? So the partial derivative is supposed to be negative, but we take them minus. So that's positive. The information function itself is positive. By the way, this is function of y data, right? Y and zeta. And so if you plug in, so if you replace zeta by zeta hat, then this is a function of data y. If you plug in, take the expectation of the information with respect to y, so this is, you take the expectation with respect to y, then this is a function of zeta, okay, only. So they start from the same concept, but totally have a different way of expressing similar concept. So the observed information is always positive because of the way, because we know that at this point is right, this point is maximum. So because of the existence of maximum, supposed to be positive. The expected information is meaningful as a function of zeta across all other miscible. By the way, the information, observed information, so Fisher information is only meaningful in the neighborhood of zeta hat. The expected information is meaningful across all admissible values zeta. So that's the difference. And the concept is that it's a average quantity of all possible data set. So this is for one realized data, right? For realized data, this is all possible data. Okay. So this is an important result, Bartlett. So sometimes this is a first order Bartlett identity, and this is a second order Bartlett identity. Basically, the scope function. So by the way, the scope function is actually this is scope function. So it actually, to be accurate, it should be written as something like this. Anyway, the proof. So how to prove this? Well, as zeta y fy zeta dy. So that's the definition. And then the definition of the scope function is this, right? So let's write it here. So this guy is a so that means if you do it, then this is actually apply the partial derivative directly, then this is this, right? So then this one, by applying this, you end up obtaining right, and then under some conditions this is actually the assumption. The assumption is that we there's under the condition that align the exchange of order of the integration and differentiation. So because of the assumption, we already assume that we can exchange the order. So then this guy is equal to 1. So the whole integration is equal to 0. I mean the differentiation is equal to 0. So that's the first part. The second part is this. So variance of S theta is S is, by the way, you can see S is actually what? Differentiation of the theta is actually vector, right? So this is actually vector. So if theta is a p-dimensional, this is actually p-dimensional vector. So we assume that theta is a column vector. So the scope function is a column vector. So then the variance is of a vector random variable is a variance covariance matrix. So that means that this is actually transpose minus transpose, right? But this is equal to 0 already, and so what we want to show, but we should to show, so we should to show that what this one, right? So we want to show this. So that means we want to show that this one is equal to so we want to show this. Okay. So so let's continue. So that means, so how to show this? Okay. So basically we start with we start with this inequality, this equality S theta y f. This is equal to 1 already, 0. Okay. So we can take the derivative still 0 transpose, and then this guy you have a theta here and here, so you can apply the chain rule. Okay. Plus, okay, plus okay. So that means expectation of right. So that's the first part is this, and the second part is actually, so here's a catch, this guy. So what's the definition of a scope function? The scope function Okay. So basically, what we end up showing is that this one is times zeta. Okay. So we basically why? Because we actually used this. That's what we showed this. So that basically gives this result. So, but this is you have a transpose. You have a transpose. So you have, which means you have a transpose here. So that basically gives your justification for okay. So what? So that means the second part is expected value of s zeta s zeta prime. Okay. So that basically uh, proved our result, because the last line is equal to 0. So that means s expected value s times s prime is equal to minus of the first guy, which is so basically this one proves this one. Okay. All right. So and then we okay. So what's the next? Well, the linearization. So if you take the Taylor linearization of this guy around zeta null, then zeta null yi plus second derivative, which is actually second order partial derivative of the scope function. So that's actually minus of the Fisher information. I mean, something like that. So 0. So roughly speaking. So that provide this result. After that, you can basically obtain the sandwich formula. Variance of zeta hat is this guy times variance of this guy times the another one, right? So that is the sandwich formula. But now, because of the this result, basically this guy is equal to information matrix zeta null. So there's a cancellation, and so you have you obtain the variance of zeta is inverse of the Fisher information. So that that's nice result of the MLE. Okay.